name is Dan Oak, and I'm a student at Athabasca University, currently taking the course Computer Science 444, Embedded/Robotic Programming. And earlier I posted on the course forum just this post reference some random notes and info I compiled after watching the Arduino for Beginners 2025 course that's on Udemy, and it's taught by Edward Renard. And there's a PDF that I posted as well. And that PDF is just this kind of random assortment of notes that I made as I went through the video. So you can see here just the Udemy videos 98 to 107 basically goes over the ultrasonic distance sensor, and I've highlighted some notes, the theoretical range, 2 centimeters to 400 centimeters, the measuring angle, that sort of thing, trigger pulse for 10 microseconds, echo pin is a high pulse to the Arduino, interrupt pins on the Arduino 1 and 2, just using time functionality and interrupts, how to calculate the distance, just a lot of different things on the notes. And I've went through, and I've made these notes sort of for different videos, not just for the ultrasonic distance sensor, so notes on the LCD screens, IR remotes, and that sort of thing. So I won't go through that too much. Suffice to say that I was asked when I posted on the course forum, would I recommend that Udemy course? And I said, yeah, I highly recommend it. And the reason being is it's not free, so it is a course on Udemy, so it does cost a little bit of money, but it's like $14.99 when you get them on sale, and Udemy courses are always on sale. And it's not a flashy course like you might find if you find some free tutorial online where someone's building something really cool, but it does do a really good job of building you up from zero to hero with the actual fundamentals of the code of the Arduino language. And in fact, there's also a section, a refresher on C and C++, which the Arduino language is built on. Another great thing about the course is that for every single circuit and project throughout the course, he does both a physical circuit with actual Arduino board and breadboard and, electrical components, whether sensors, actuators, effectors, all that sort of stuff. And then for every actual hardware circuit he builds, he also goes through the exact same code and builds the circuit, a simulated circuit in Tinkercad. So you could follow along with the entire course and not even have an Arduino or any electrical components and just follow along in Tinkercad. So I think it's a really good course. Another thing that I really like about it is as he goes through the courses, he kind of builds it up incrementally, but he teaches best coding practices. So, which you don't always find in the free tutorials. They kind of sometimes just want to get the code out to you so they can show you the end build. Whereas he takes a lot of time to show you the best coding practices. So, for example, I'll just kind of go through a couple of the little bits of code that he has here. So this is code that I took right from the course, because he includes the code and the resources as you go through the videos. And the idea here is that he's a big advocate of using time functionality to avoid using the delay function. So if you're familiar with the Arduino coding language, you know the delay function halts the code. So it stops the code for whatever number of milliseconds you pass in. So again, it takes a single parameter of type int, which represents the number of milliseconds that you want to halt the code for. So if you pass in 1,000 to the delay function, you stop the code for 1,000. So it's blocking code. It doesn't support multi-threading. And although multi-threading is not actually a thing in microcontrollers, the idea is still there. Like, it doesn't allow you to do multiple things at once, like have multiple LEDs blinking at different rates, for example. So I'm just going to quickly kind of compare the code side by side and show you what I mean. So the original code using blocking delay function. So I won't go through the code too much because you can pause it if you need to. But basically, this code, it defines an LED pin, and then it defines this constant. Well, correction, it's not a constant. There's no const keyword, but it just finds this variable blink delay as 500, so representing 500 milliseconds, half a second. We declare a variable for the LED state, set it to low. In the setup, we set up the serial monitor with a baud rate of 115,200, and we do serial.set timeout to 10. So this overrides the default timeout, which I believe is, I want to say 1 second, or I might be off on that. That is mentioned in the Udemy video series, so if you watch it, you'll probably learn. And hopefully not forget like I just did. But and then you set up the pin mode. The LED pin is an output. In the loop, this is just some validation. So that basically we're checking the serial monitor and seeing if someone types something in. And then we're using the parse in function to grab the string data that's on the serial monitor and assign it to an int variable. And then we're just checking that to see if it's between 100 and 400, 4,000 inclusive, meaning between 1/10 of a second and 4 seconds inclusive, and assigning that to the blink delay. So we can change the blink delay. Instead of being 500 milliseconds, we can just change it. That's all that code's doing. Down here, we're simply checking the state of the LED. If LED state equals low, then we're going to change it to high. Else, meaning if it was already high, we're going to set it to low. So we're just toggling the LED state and then writing, using digital write to write the LED to the LED pin, whatever that LED state was. And then we're calling the actual delay function, which is blocking code, delay function passing in blink LED. So let's say if I hadn't wrote anything in the serial monitor, it would be 500 milliseconds. So I'm actually delaying the code for half a second, 500 milliseconds every loop. So that is blocking code. And in this particular case, it's fine. There's nothing else happening besides blinking this LED. So there's absolutely nothing wrong with it. But if you want to do, multi-threading, that would cause issues. You wouldn't be able to. So this is the exact same code, but I've replaced the highlights here, i.e. the blink delay, 500 milliseconds, and the delay function being called here, with time functionality code, which is non-blocking code. So basically, I'll just make this a little bigger here. Basically, we declare a couple of variables of unsigned long. Now, first of all, why unsigned long? Well, because we're dealing with time. And so time, especially with milliseconds, adds up very quickly. Again, if you use an int, you have a range of about negative 32,000 and 700 and some to positive 32,700 some. So right away we're going to use a long because that gives us negative 2 billion to positive 2 billion of a range. But again, when you're dealing with milliseconds, every 1,000 milliseconds is a second. So it wouldn't take that long theoretically to get past 2 billion, depending how long this is running. So we're using an unsigned long because unsigned long basically says, hey, we're not ever going to have a negative number in here. So any of those values that you were going to give me in the negative, that negative 2 billion, just add that, tack it on to the positive side, to the front. So now I have a range from 0 to 4 billion. So that's why we're using unsigned long. That's a fairly common convention when dealing with time. So we create a couple of variables, unsigned long, previous time LED blink, using the millisecond function to grab that, and then unsigned long blink delay equals 500 milliseconds. So again, just creating my constant, or my variable in this case, because I'm not using the const keyword, my variable for my blink delay, and I want it to be half a second. But this is the important thing here. Right when the program starts, this millisecond function is going to return the time in milliseconds that is elapsed since the program started. At this point, it's going to be 0 when the program first starts, but we'll see how that is going to be used throughout the code. All the other code is the exact same. Here's the thing. When we come in the loop function, after we do this, user input thing, if we want to change the blink delay, every time we come in the loop function, we're going to call the millis function and assign that to a local variable of unsigned long called time now. So we're getting the current time, the time that's elapsed in milliseconds since the program started, every loop. And then we're going to see if we're going to do some time functionality code here to see if we should execute any code. Basically, this is acting as our delay function, but it's non-blocking. So we're going to go if time now, which is the time that we grab, the current time every loop, if the current time, based on this time now variable, minus the previous time the LED blinked, so the last time the LED blinked, if this duration, the current time minus the last time the LED blinked, if that duration is greater than blink delay, which is, something we set, in this case 500 milliseconds, so if it's greater than half a second, if half a second has passed since the last time the LED blinked, let's do something. In this case, again, check what the LED state is and toggle it. And then write that LED state to the LED pin. And then we're going to update the previous time LED blinked by incrementing it by blink delay. Now, as I said, when he does the code in the videos, he incrementally builds it up. So at first, he doesn't go right to blink delay. I've kind of went there in this video, but he would have incremented by time now. Or he, not even incremented, he just assigned time now to the previous time, because it kind of makes sense. Think about it. We just got the time, and if I assign that to the previous time LED blink, well, I know the LED is blinking right now, right here. So it makes sense intuitively to assign the current time, time now, to blink LED. The problem with that is it works fine the first time, second time, a lot, for a while, but there is a non-zero amount of time that's happening here. This code does take some time to execute. It's not a lot. Processors are quick, but it is a non-zero amount of time. So, and it might be different every time depending what the microprocessor's doing, if there's other things happening. So you end up getting this time creep, where you will slowly get off your mark. So instead of, being let's say if this was a 1,000 milliseconds for ease, instead of being 1,000 and 2,000, it might be 1,000 and then 2,001 and then 2,000 or 3,004, and you might slowly add a little bit of milliseconds on every iteration, and over time that adds up. Eventually you might be off by a whole second or something, which can be significant. So instead of doing that, we're just always going to increment the previous time LED blinked by a constant, whatever the blink delay is. So we use the compound operator to do that. And that's all explained in the video, and he goes through the transition of starting with time now and then doing this. This code is exactly as stated above. It's just, again, the reason for using time functionality, non-blocking code, is to kind of achieve multi-threading. Even though multi-threading, again, is not a thing in microprocessors, the idea of it doing, simultaneous tasks concurrently and asynchronously is a thing. So, having LEDs blink at different rates, for example. So all this code is showing is that we've, everywhere where we had, one LED, like, in our defines and here, we have two. So we have 2 times this time functionality code, the previous time LED 1 blink and the blink delay. We only have to grab the time once. So every loop, when we come in the loop, we do we declare and initialize our local variable of onSign long, time now, 2 milliseconds, called the millisecond function, which returns the current time that's elapsed since the program started. We only have to do that once in the loop, and we use that same time in both if statements. And again, each of these if statements is the same as before. It's just finding out the duration between the current time that you just, of this loop, the current time minus the previous time that the LED blinked, seeing if that duration is greater than whatever you've decided is a blink delay, which again, you have 2 different blink delays. You can set these individually. Like up here, I have a blink delay of 500 milliseconds and 700 milliseconds respectively. And then you do some code and then, update your previous time LED blink. He was also big in using time functionality interrupts and a complementary filter, math, which is just math, to improve the ultrasonic distance sensor reading and accuracy by ignoring outliers, meaning readings that are just, they're not accurate, they're just erroneous readings, and mitigating sensor interference. So again, I'm going to go over the code quickly, but I'm going to focus on the highlighted parts. So again, we've got all of our defines up here, all of our constants. We've created 3 constants for our 3 LED pins, and we've created a constant for our echo pin and our trigger pin. Again, these are the 2 pins besides your VCC and your ground, your power and your ground. These are the 2 pins associated with the HC-SR04 ultrasonic distance sensor. Your echo pin is your input pin, your trigger pin is your output pin. We've got our time functionality here, our 2 variables of type onSign long. Last time ultrasonic trigger, again, we use the millis function to grab the current time. And we're creating a variable for the delay, so ultrasonic trigger delay. We passed in 60. If you look at the data sheets, some people use 60, some people use 100, but don't do less than 60 milliseconds for your ultrasonic trigger delay. Okay, trying to be quicker than that will cause issues. And really, for any of the projects you're likely to do, updating the distance measurement reading every 60 milliseconds is more than fine. I mean, you're not going to probably be having anything that's going that quick that needs to be that accurate where you need a reading like that. This code also has to do with some of the time functionality, but it's going to be updated. These variables are going to be updated inside an interrupt. So that's why we have the volatile keyword in front of each variable. Volatile keyword, just anyone familiar with multi-threading in Java or C++ knows that the volatile keyword is kind of a way to have thread safety when you have a shared resource that's going to be updated across threads. And although multi-threading is not really a thing in microprocessors, whenever you're going to be doing updates to variables in interrupts, you need to include the volatile keyword for similar reasons. So We've got a volatile unsigned long, pulse in, time begin, pulse in, time end. Again, these are just going to be both things that store time in milliseconds. And if you're familiar with the HC-SR04 ultrasonic sensor and you use the library that typically one would use when using that, you'll probably be familiar with this pulse in. That's a function that typically is used in order to get the duration, which you're going to use in your distance calculation. So you'd create something like this. You'd create a variable double duration milliseconds, or microseconds rather, because if you read the data sheet, it returns the duration in microseconds, not milliseconds, equals, you'd call a pulse in function, and you'd pass in some, either the pin number directly as a magic number or some variable representing the echo pin. That's typically what you use, but this has the same negative effects that the delay function does. Okay, so the pulse in function is a blocking function, so it's blocking code just like delay. So and then we're also creating a new distance available Boolean variable. So we're creating this Boolean variable just to let us know if there's a new distance measurement to be taken. So again, we don't want a distance measurement constantly. We only want a distance measurement every 60 milliseconds or so. So we'll set this false initially. Then this code here, double previous distance equals 400. This is associated with the ignoring the outliers. So if you remember from the code I showed you before, the range of the ultrasonic distance sensor is between 2 centimeters and 400 centimeters. So anything outside of 400 centimeters is going to be an erroneous reading because the distance sensor doesn't read past 400 centimeters. So basically, if you get like a reading of 700 centimeters or whatever, it's wrong. So that's an outlier and we're going to ignore it. So we're going to ignore that by creating this variable of type double called previous distance and setting it to 400. And that'll become more clear as we go down. Now, in the Udemy course, you'll know he's a big advocate of using constants everywhere. He doesn't like magic numbers. And again, it's best coding practice not to use magic numbers. Now, this is code that I took directly from his resources, so he did use this. And this is fine. In this case, it might be that we really know what this is, and maybe a comment could help solidify this, an inline comment. But really, it probably would have been better up here to do a pound define or use the const keyword and create a const int, representing max distance of ultrasonic sensor or max range or something called 400. But that's fine. We know what it is for now. This method is just a helper method, trigger ultrasonic sensor, takes no arguments in, it's a void method. And it basically, again, if you remember the notes, we need to output a trigger pulse for 10 microseconds. That's how the ultrasonic distance sensor works. So what do? Well, first we're going to do a digital rate of the trigger pin low first, and we're going to delay microseconds. This is the delay microseconds function, not the delay function, which is in milliseconds. Delay microseconds for 2 microseconds. And why are we putting it low? That's just so we can put it in a known state. The actual work is being done right here. We're doing digital rate of the trigger pin high for 10 microseconds. Again, this is delay in microseconds because that's how the ultrasonic distance sensor works and what the data sheet calls for. And then we set it low. So that's when we send that output. This is how the function works. So that function is going to take care of that for us. The distance function, how does that work? Well, it takes no arguments and it returns a double, which is going to represent the distance. And how does that work? Well, again, this is all in the data sheet of how to do this, and he explains it in the video. But essentially, normally, here's where you'd have that pulse in function. You'd call the pulse in function associated with the library. That does all the work behind the scenes, this pulse in function that takes in the pin associated with the echo pin, and it's going to return a double representing the duration of microseconds. So that's what's happening. In this case, these are going to be microsecond values. So these are going to be microsecond values and not milliseconds, microseconds. And we're just going to take, same as we did in the other time functionality, where we took the current time minus the previous time. We're essentially doing the same thing here. They're just named a little different. We're going the pulse in time end, the end time, minus the pulse in time begin. This is going to give that duration, the duration that the pulse was high when you send out a pulse. So this is going to give us that duration of pulse, and we're going to assign it to a double, which we're naming duration micros, because again, this just represents microsections. So make sure your names are, indicative of what the, they're proper names. They're named properly, so, they're kind of self-documenting. You notice there's no inline comments in the code here. So you want your code to be self-documenting. And then you're just going to actually calculate the distance, because this gives you the duration that the pulse was high. Then you're going to calculate distance. Double distance equals duration in microseconds, which is this variable here. You're going to divide by 58 if you want the distance in centimeters, or 148 if you're a big fan of the imperial system and you want it in inches. And again, all this calculation is in the data sheet, and I go over this in my videos online, and I believe he goes over it as well in his Udemy course as well. But suffice to say for now, doing this calculation, you'll get the distance in either centimeters if you divide by 58, or inches if you divide by 148. And then we have if distance is greater than 400, meaning again, we know that greater than 400 means it's out of range because we only go to 400 centimeters. If the distance is greater than 400, we're just going to return the previous distance, which is 400. We're basically going to return the max thing. If the distance is reading greater than 400, we know it's an erroneous reading, the thing's too far away, just return previous distance, 400. That's all we want to return. And we escape. We escape this function. Otherwise, we're going to move on, and we're going to go distance equals whatever the previous distance was times 0.7, so we're going to get 70% of the previous distance. We're going to add to that the current distance that we just read, right? We're going to read the current distance times 0.3, so 30%. So we're basically doing, this is called a complementary filter. We're doing a complementary sort of average where we take 70% of the previous distance, 30% of the current distance, we add them together, and that kind of gives us an average. Now, the reason we would do this is so we can smooth out signals. So basically, if you hooked up the ultrasonic distance sensor to an oscilloscope, or you just, output the readings to a serial monitor, you might notice occasionally you just get these really weird erroneous errors. So even if we're limiting ourselves to within the 400, we still might have signals jumping from time to time, jumping up and down. So if we want to smooth that out, we do an average between the previous distance and the current distance. Now, you can mix up these numbers. You could make the previous distance 0.9, taking 90% of the previous distance and only 10% of the current distance. That would mean that you'd have a very smooth transition. You'd have like no blips, but it would be slow to react. Basically, if something jumped in front of the ultrasonic distance sensor, it wouldn't react, and the signal wouldn't change as quickly. Alternatively, if you only took 10% of the previous distance and 90% of the current distance, you would react really quickly, but again, you wouldn't get the same filtering which is the whole point of doing this. So, you can mix up, you can play around with the percentages a little bit, but, kind of convention is to use this 70% of the previous distance plus 30% of the new distance, and that gives you the best of both worlds. It gives you a smooth signal, but still responsive enough for most applications. And this is explained in detail in his videos. We assign that to distance. We update the previous distance to whatever the current distance is that we just got, and we return it. That's all happening there. Now here's the meat and potatoes of this lecture. The interrupt. He says to use interrupts as opposed to delays. So how do you do an interrupt? Well, you need to create an interrupt function. And interrupt functions are created with no arguments. They don't take any parameters, and they're void. And then you just do whatever code you want in there. But again, any variables that you're changing in here need to have the volatile keyword for safety. So we're creating a function we're going to call echo pin interrupt, because again, it's going to be an interrupt on the echo pin. And that's why we've set up the echo pin 2, pin 3. The two interrupt pins on the Arduino are pins 2 and 3. And then, so when this interrupt function gets called, we're going to go if digital read of echo pin equals high, meaning again, the echo pin, if the digital read of the echo pin is high, meaning we just, we had a high pulse, now we're up here. If it's high, we want to start measuring. So basically, when we come up here, we have low pulse and then we go high. When we send out the trigger, we want to start measuring right here. So we're going to do pulse in time begin, which is that unsigned long we created, volatiles, because it's going to be changed in an interrupt. We're going to call the microsecond function, which is like the millisecond function, but it returns microseconds, which is how the ultrasonic distance sensor works. Else, meaning if digital read of echo pin is low, because that would be the else, then we're going to stop measuring. We're going to go pulse in time end equals microsection again. So again, if you picture, and he does this in the video, he draws it out. I just don't have the capability to do that right now. But the pulse would be low, the trigger pin is low, and then we send the trigger pin high, pulse high for a certain duration, well, 10 microseconds, and then it goes low. That's what we send it. And when this is coming back, we're getting a high pulse back. So the high pulse back, as soon as we read a high pulse, when this gets interrupted, when some pulse comes back in on the echo pin, and this interrupt happens, which I'll explain why that happens in a second, but when there's a change on the echo pin, which is the interrupt pin, as soon as we read that something's high, we want to start measuring. And then we want to measure until the pulse goes low. We want to measure how long we had a high pulse, because that represents the duration in microseconds, which we use to calculate the distance. Also in here as well, when we stop measuring, we want to set the Boolean variable new distance available to true, because we want to say, hey, we just did a measurement. We went from high to low. We measured the duration of a high pulse that came into the interrupt pin. So yeah, there's new distance available. Now, when is this method going to get called? When is this interrupt function going to get called? We know we're doing things right. We've got the echo pin on pin 3. Pins 2 and 3 are the interrupt pins. You'll know this if you watch this video, the Udemy course. Pins 2 and 3 are the interrupt pins. We know that we have to set up an interrupt function. We can name it whatever we want. By convention, you name it something interrupt, and typically the pin interrupt. And it can't have any parameters, and it's void. And then in there, you can do whatever you need. And if you're going to manipulate variables inside the interrupt, they need to have the volatile keyword appended to the front of them. But when does this get called? Well, let's skip ahead of this. This function is just power LEDs from distance. This is just turning on a particular LED, one of the 3 LEDs, based on the distance. So we don't need to go over that. Here's where everything's happening. In the setup function, after we set up our serial.begin using this baud rate, and we set up our pin modes, the echo pin is an input and the trigger pin is an output, and then all of our LEDs as outputs, we call the attach interrupt function. So the attach interrupt function, this is how we use interrupts. Attach interrupt takes in 3 arguments. It takes in digital pin to interrupt, so we make a call to the digital pin to interrupt function that takes in as its parameter argument, it takes in the pin that is going to be that's the interrupt pin. In this case, it could be pins 2 or 3. In this case, we're going to interrupt on pin 3, one of the interrupt pins, which is where the echo pin is attached. So that's the first argument. You make a call to digital pin to interrupt, passing in the pin that's going to be interrupting. Comma. The second argument is the function that you want to execute when the interrupt happens. Echo pin interrupt. That's the one we created. So that's this function here. Now, if you're making a function call, why do we not have parentheses here? Well, you're not actually making the function call here. It's saying call this function. So we don't want to put the open close parenthesis here, because that's actually an operator to call, like that basically says call this function. So you put the function name, but minus the actual parenthesis. So that's just a syntactic thing, just to remember. And then finally, you put when the interrupt is going to happen. You could put various different constants in here: high, low, rise, fall. I think there's a couple different ones. Change. We just wanted to interrupt whenever there's a change. That way it interrupts if the signal's high and when it's low. That way we can measure the duration. That way this gets called when it's high. It comes in and gets called. Hey, digital read of echo pin equals high. And then we set the pulse in time. And then, a couple microseconds later, it happens again, because again, this interrupt gets triggered on a change, not a high or a low, any change. And when we come in later, oh, it's on a low pulse now. So if digital read of echo pin equals high, no. So instead, it's low, and we're going to set the pulse end time and set new distance available to true, this Boolean flag that's going to allow us to do our distance reading. So that's how we set up an interrupt. In the setup function, we call this attach interrupt function, passing these 3 arguments: digital pin to interrupt, passing in one of the pin that's on one of the interrupt pins, 2 or 3 of the Arduino, Uno or Nano. We pass in the name of the function. That's the interrupt function we've created. Again, don't include the open close parens. Don't do that, because that will actually call the function. You're just indicating the function here. And then pass in a constant to indicate when you want this interrupt to happen. If we just passed in high here, it would only interrupt when there was a high pulse. That's not what we want. We want it to interrupt whenever there's a change. And then the loop function, we do all of our regular time functionality stuff. We create a local variable of onSign long time now and set it to the millisecond function, grabbing the current milliseconds that have elapsed since the program started. And again, instead of using a delay function, which is blocking code, we go if time now minus last time ultrasonic trigger, right, is greater than some ultrasonic trigger delay, some constant that we created, that we decided, and we said 60 milliseconds rather. Remember, that could be 60 or 100 or something like that. Those are kind of the typical values. Don't put it less than 60. It's not recommended by the data sheet, nor are you ever going to need it to. You're never going to need measurements that quick. That you need a measurement every 60 microseconds for anything you're probably going to be doing if you're watching this video. So again, this just says if this duration is greater than that delay, we're going to update the last time the ultrasonic triggered to we're going to, by this delay amount, again, not using the current time, but by this delay amount, so it's constant. And then we're going to call the trigger ultrasonic sensor. So basically, every, in this case, 60 microseconds, we're going to call the ultrasonic sensor function, which basically sends out a pulse, a high pulse out of pin 4 for 10 microseconds. And we're doing that every 60 microseconds. Sorry, we're sending out a pulse for 10 microseconds, and we're doing that every 60 milliseconds. I know there's a lot of talking going here, but again, this is to advocate to go to that Udemy course. He does a much better job of it than I am doing it here. And then basically, also in the loop, we're going to go, so if new distance available, meaning if that Boolean flag is true, first of all, we're going to set it to false, and now we're going to get the distance measurement. So get ultrasonic distance, this returns the double, represent the distance, based on that calculation all up here, using our filtering and everything. And then we're going to, call that power LEDs from distance function. So we're going to turn on, one of the red, green, or blue LEDs based on the distance that the object is from the ultrasonic distance sensor, and print it out to the serial monitor. That's all that's happening. And again, this gets set false as soon as we come here, but every time we jump in the interrupt function, when we jump in an interrupt function, if we have a high pulse, we set pulse time in, and then a few microseconds later, when we hit this interrupt function again and execute it again, we assign some value to pulse in time end, but then we set this to true. So every 60 milliseconds, we're going to have a new distance available. And that's essentially the code there. It says, basically, he says, avoid delays whenever possible. Delays are acceptable in certain circumstances, like in the setup function, when the setup function is only running once, so it's not going to constantly delay the code. Sure, throw a delay in there. Or if you have small microsecond delays, not milliseconds, microsecond delays here and there. But in this case, even though we're doing the trigger pulse is only 10 microseconds, it's happening every 60 milliseconds, so it actually accounts for a fair bit of time. But if you're only having a 2 microsecond delay every couple seconds, well, that'd be nothing. It probably wouldn't be worth the complexity to do this time functionality and interrupts, just throw in a delay. So there, like everything, there's a time and a place for it. But basically, this is just kind of a quick sample of the type of code you can expect, and really the principles and the best coding practice that he tries to push. Now he does a better job. He shows he's got a circuit in the background that he's building. He's got he's doing a Tinkercad circuit, and he's doing this better because he's a professional, unlike me. But that's just my quick little rant on why I think it's a good course, and it teaches good coding practices, best coding practices really. And that's just one of the type of things, using time functionality instead of delay blocking code, and using interrupts. And another reason I did this too is because part of the course mark is to collaborate or to do post things in the course form. And sometimes I find it difficult to post things in the course form. So you know what? Someone asked, hey, is it a good course? Yeah, it is, and here's why I think it is. So anyway, thanks for watching, and hopefully you learned something.